These are the four oxoanions, oxacids of chlorine, hypochlorite, chlorite, chlorate, and perchlorate ions. Now I am comparing ClO bond length values among these four anions. In perchlorate ion, we have more multiplicity. If we have more multiplicity, definitely bond length will be less. That's why bond length order is 1 greater than 2, greater than 3, greater than 4. Suppose I am asking bond order here. Then for this perchlorate ion, bond order is equal to total 7 bonds are there. So 4 surrounding atoms, 7 by 4. And here bond order is equal to 5 by 3. Here bond order is equal to 3 by 2. Here bond order is equal to single bond. So more is the bond order here. Automatically less is the bond length. So 1 greater than, 2 greater than, 3 greater than 4 is the correct order of bond length values. Next, HOCl, HClO2, HClO3, HClO4 in the order of acidic strength. Then this is the order of conjugate base strength. Weak acid, strong conjugate base. So remove hydrogen and becomes anion, conjugate base strength minus. Conjugate base strength. Next point. HOCl, HClO2, HClO3, HClO4. Now I am writing thermal stability order. So thermal stability for covalent compounds depends upon bond dissociation enthalpy, bond enthalpies. For ionic compounds, thermal stability depends upon mainly lattice enthalpy. So for covalent compounds, bond enthalpies you have to compare. Out of these 4 compounds, in HClO4 we have more number of multiple bonds. More multiplicity is there. Therefore, for breaking bonds in HClO4, we require more energy. That means HClO4 is thermally more stable. Therefore, HOCl less than, less than, less than. So HOCl is thermally least stable. Therefore, it is highly reactive species. That's why in number of chemical reactions, HOCl is a very good, strong oxidizing agent. That's why here, one property I am comparing with respect to thermal stability, that is oxidizing power. Greater, greater, greater. గా మనం ఏమనుకుంటామంటే మోర్ ఈస్ ద ఆక్సిడేషన్ స్టేట్, strong oxidizing capacity. Generally, that is applicable, but that statement is not applicable here because HClO4 chlorine is in +7 oxidation state, but weak oxidizing agent. HOCl chlorine least oxidation state, but strong oxidizing agent. So this comparison on the basis of thermal stability. కొంచెం మనం ఓకేనా, కొంచెం కన్ఫ్యూజన్ స్టేట్మెంట్ ఇది. లైక్ మనకి ఫాస్ఫారిక్ యాసిడ్స్ వచ్చినాయి కదా, ఎసిడిక్ స్ట్రెంత్ H3PO2, H3PO3, H3PO4. They're also on the basis of Ka values only we compared acidic strength. Similarly here, oxidizing power don't go to according to oxidation state. We have to compare with respect to their thermal stabilities. So exceptional property none of this one. Last one, hypochlorous acid, chlorous acid, chloric acid, perchloric acid, oxidizing power on the basis of their thermal stabilities. Thermal stability is on the basis of multiplicity of the bond. More multiple bonds, more is energy required for breaking the bonds. Next, I'm taking Cl2O molecule, O central atom, chlorine surrounding atoms. Cl2O, it's a bent molecule. Bond angle value is experimental value 111 degrees. Electron pairs. Next one, ClO2 molecule. This is also bent molecule. The bond angle of 117.6 degrees. This is odd electron molecule. Paramagnetic substance. Chlorine 7 valence electrons, 2 oxygens, 2 into 6, 12 plus 7, 19 valence electrons are there. So odd electron molecule, paramagnetic species. And in this we have Cl, double bond O, day 2 bond O. A total 7 plus 2 into 6, 19 electrons. 9 pairs we have to accommodate. So 9 pairs means first pair, my second pair, third, fourth, fifth, sixth, seventh, eighth, ninth, and one odd electron. That chlorine odd electron. And one more possibility, that odd electron, because oxygen is more electronegative and small size. That odd electron more concentrated near oxygen. Whereas in NO2, that odd electron concentrated near nitrogen central atom. Whereas here, odd electron is concentrated near oxygen because of its small size when compared to chlorine and high electronegativity when compared to chlorine. That's why, since odd electron is more concentrated near oxygen, does not undergo dimerization. Very special property of ClO2, very, very important property. Generally, all electron molecules undergoes dimerization, but this is one compound where even though odd electron is there, it does not undergo dimerization because odd electron is not concentrated near central atom. Surrounding atom is very small size when compared to chlorine, and that too, it is second most electronegative element. That's why that odd electron is more concentrated near oxygen. Or odd electron involved in odd electron is not localized near central atom. That point also I am writing here. Odd electron is not localized near central atom. That's why, like other odd electron molecules, this compound does not undergo dimerization. Next point, Cl2O6, Cl2O7. Cl2O6. Cl2O7. Cl2O6. One more structure also they proposed where oxygen act as a bridge between two chlorines. Day 2 bond. Day 2. So structures wise, first two compounds important. Cl2 and ClO2. Both pent molecules, both bond angles are more than tetrahedral bond angle, 111 in Cl2O and 117.6 in ClO2 molecule. This is the important information related to very big concept oxides and oxyacids of nitrogen, phosphorus, sulfur and chlorine. Actually, we started with hydrides. In those hydrides, we discussed about only covalent hydrides. In addition to that, we have one category called ionic hydrides. Let us discuss few points about these ionic hydrides. These ionic hydrides, also called as salt-like hydrides, also called as saline hydrides. Salt-like hydrides, saline hydrides means on the basis of the structure. That means structures of these compounds are similar to rock salt structure, sodium chloride type structure. That's why these compounds are called salt-like hydrides or saline hydrides. Salinity means sodium chloride. Now let us move to a few points about these ion hydrides. So the first point is compounds of hydrogen formed with most of the S block metals. Except beryllium and magnesium. Hydrides of beryllium and magnesium. Polymeric hydrides. We have three important elements form polymeric hydrides in main group elements: beryllium, magnesium from S block, and aluminium from P block. Those three element hydrides are polymeric hydrides. Next point. Among these ionic hydrides, lithium, sodium, potassium, rubidium, and cesium hydrides, first group hydrides. Less. This is the order of ionic nature. Pajan's rules. Big size cation. Big size cation, more ionic. Next, lithium, sodium, potassium, rubidium, and cesium. Now I am asking, thermal stability order. So more ionic means don't say thermally more stable. So thermal stability mainly decided by their lattice enthalpies mainly. Main factor is lattice enthalpy. Or thermal stability of ionic compound decided by packing of ions in the crystal structures. Effective packing of ionic crystals, if you have, those ionic compounds are thermally more stable. Generally, small size cation with small size anion, large size cation with large size anion form most effective crystal packing. That means ions are of comparable sizes form effective crystal packing. If one ion is very small, if another ion is very big, that packing is not efficient. Ions are of comparable sizes form effective packing. Comparable sizes means small cation with small size anion, large size cation with large size anion form effective crystal packing. Based on that, this is reversal. This is thermal stability order. Lithium hydride more than sodium hydride. So side by side I am writing both statements. Generally, one confusion are giving more ionic means thermally more stable. That is wrong. More ionic is different. Thermally more stable is different. More ionic or less ionic are decided by Pajan's rules. Thermal stability of ionic compounds decided by crystal packing of ions. Next point. These ionic hydrides crystalline compounds like other ionic compounds, non-volatile because they have very high boiling points. Ionic compounds like other ionic compounds, non-conducting in solid state like other ionic compounds. If you take molten solution, conduct electricity due to the availability of free ions, mobile ions, and this molten solution on electrolysis we are getting hydrogen gas at anode. Generally, hydrogen obtained from H plus ions near cathode, but here hydrogen gas is obtained from H minus ions. That's why near anode hydrogen comes out. In all electrolysis reactions, hydrogen obtained near cathode is wrong, except in the case of hydrides. Hydride ions loses electron and gives hydrogen gas at anode. And these ionic hydrides, like other ionic compounds, react violently with H2O, producing hydrogen gas, and solution becomes alkaline. React violently with H2O, producing hydrogen gas and alkaline solution. Example, suppose I am taking sodium hydride plus H2O plus sodium hydride Na plus H minus, H plus OH minus water. So OH minus goes to Na plus and H plus go to H minus. Therefore, we are getting H2 plus NaOH. So ionic hydrides, aqueous solutions, are alkaline in nature with the liberation of hydrogen gas. That means these compounds act as a good hydrogen supplier. Hydrogen supplier means these ionic hydrides act as reducing agents also. Act as reducing agents. Out of these ionic hydrides, lithium hydride, it has very important property. That lithium hydride, we are using one point I am writing related to lithium hydride. This lithium hydride used in the synthesis of other useful hydrides. Lithium hydride on reaction with aluminum chloride, it forms very useful compound LiAlH4. On this lithium hydride on reaction with the diborane, it forms very useful compound LiBH4. Lithium aluminum hydride, lithium borohydride. Now these compounds act as reducing agents. If you observe the second group hydrides, calcium hydride, suppose plus, so ionic hydrides liberate hydrogen gas and gives alkaline solution, calcium hydroxide. Calcium hydride is commercially called as hydraulic. These are the a few points related to ionic hydrides, mostly formed by S block metals except beryllium and magnesium. And one more point I am writing here. Among ionic hydrides, significant covalent character. Significant covalent nature. So for covalent nature, we need small size cations. Therefore, three compounds have significant covalent character. Lithium hydride, next beryllium hydride, next magnesium hydride. These three compounds have significant covalent nature. Ionic hydrides only, but covalent nature. That beryllium, magnesium, significant covalent nature, and polymeric hydrides. So these are the few points about hydrides, oxides, oxyacids. Okay. In the main group elements, we have one more small topic is there. It is fluoride xenon. Three compounds we have in the fluoride xenon. XCF2, XCF4, and XCF6. First point is structures. sp3d, sp3d2, sp3d3, linear, square planar, distorted octahedral, 3 lone pairs near central atom, 2 lone pairs near central atom, 1 lone pair near central atom. Out of these 3 compounds, 2 compounds symmetrical structure, that is XCF2 and XCF4. Therefore, XCF2 and XCF4, for these 2 compounds, dipole moment is equal to 0, whereas mu means not magnetic moment here, dipole moment for XCF6, mu is not equal to 0. Structural information, simple one. Next point, XCF2, XCF4, XCF6. They can react with F minus donor, also with F minus acceptors. That means they can donate, they can accept. F minus donation, F minus acceptor. So a few examples I am writing here. F minus donors, F minus acceptors. Suppose I am writing XCF4 plus BF3 is given. XCF6 plus SBF5 is given. So BF3, SBF5, they can accept F minus ions, because for boron, maximum covalency 4, for antimony, maximum covalency 6. That's why in this case, XCF4 and XCF6 act as F minus donors, or BF3 and SBF5 are called as F minus acceptors. So these are 2 reactions supporting fluoride xenon reacts with F minus acceptors. Then XCF4 becomes XCF3 plus, and BF3 becomes BF4 minus, and XCF6 becomes XCF5 plus, and SBF5 becomes SBF6 minus. So we are getting cationic species here, xenon compounds. XCF3 plus 7 electrons, 4, 5, 6, 7. Positive charge, 1 removing 1 electron. So 3 fluorines, 3 fluorines, 2 lone pairs. Total 5 pairs are there. 5 pairs means sp3d2 hybridization, sp3d hybridization. In sp3d, 2 lone pairs. In sp3d, 2 lone pairs means this is T-shaped mark, T-shaped species. Next we have XCF5 plus. Okay, so once again 7 electrons, 1, 2, 3, 4, 5, 6, 7, and 5 fluorines are there. 5 fluorines and 1 lone pair. So total 6 pairs are there. 6 pairs one lone pair. Therefore, sp3d2 hybridization. In sp3d2, one lone pair becomes square pyramidal structure. Two examples, important examples supporting reaction with F minus acceptors. Similarly, these compounds reacts with F minus donors also. Next, one more example I am giving. XeF6 I am taking. For example, I am giving rubidium fluoride. So RBF is ionic species, donates F minus to XeF6. So now RBF is called as F minus donor. So XeF6 now becomes F minus acceptors and gives very special compound RB2 XeF8. Now please highlight this compound RB2 XeF8. Two compounds we have with this formula: CSF, CS2 XeF8. My anion I am highlighting, that is XeF8 2 minus ion. Hybridization is not applicable for this species XeF8 2 minus, but experimentally this structure is called as square antiprismatic. Square antiprismatic means middle center, in the middle we have xenon, top 4 fluorines, bottom 4 fluorines. Center xenon, top 4 fluorines, bottom 4 fluorines. XeF8 2 minus. The structure is called as square antiprismatic structure. 1 minute, I will show. This is the shape of antiprismatic, square antiprismatic. Central is xenon atom. This is xenon. This is xenon. The top 4 fluorines, bottom 4 fluorines. With this shape, we have two important species. One is with the rubidium, another one with the cesium. square antiprismatic structure obtained when XeF6 reacts with fluoride ion donors. Next point. Hydrolysis reactions of fluoride salt xenon, xenon difluoride hydrolysis in basic medium gives Xe plus HF plus O. XeF4 on hydrolysis gives Xe plus HF plus O2 plus very explosive compound XeO3 is obtained. XeF6 plus H2O gives XeO3 plus HF. Important hydrolysis reactions of fluoride of xenon. Out of these, first two are redox reactions. This is non-redox reaction. The second reaction is disproportionation reaction with respect to XeF4. Xenon plus 4, xenon 0, xenon plus 6, xenon trioxide. Hydrolysis reactions of fluorides of xenon. In this, one hydrolysis reaction I am highlighting, that is XeF6. XeF6. So during hydrolysis, in place of fluorine, OH and OH, then HF comes out. From water, OH replaces fluorine and fluorine with hydrogen form HF. And between these two, elimination of water takes place. Thereby, we are getting XeOF4, first step. Next step, two more fluorides, two more hydroxides, and another elimination of water. Then we are getting XeOOF2 or XeO2F2. The next step, OH, elimination of water. Then we are getting XeOOO, that is XeO3 finally. That means stepwise hydrolysis reaction. XeF6 with H2O, first it form XeOF4 plus HF. In the next step, XeOF4 plus H2O, it gives XeO2F2 plus HF. In the next step, XeO2F2 plus H2O finally gives XeO3 plus HF. Two HF, two HF, two HF. If you add, we are getting final reaction. XeF4 plus 3H2O gives rise to XeO3 plus 6HF. These are called as stepwise hydrolysis reactions of XCF6. Two important intermediate compounds, please highlight. One is XCOF4, another one XCO2F2. XCOF4, XCO2F2. Xenon and the four fluorines, oxygen. So one lone pair. 1, 2, 3, 4, 5, 6. So sp3d2, one lone pair. Square pyramidal structure. XCOF4, XCO2F2, two fluorines, two oxygens. 1, 2, 3, 4, 5. So sp3d hybridization, one lone pair, seesaw structure. According to Bent rule, more electronegative atoms in axial position. XCO2F2 intermediate compounds obtained during the stepwise hydrolysis of XCF2 XCF6 reaction. Next, one more point we have. XCF6 complete hydrolysis. XCF6 on complete hydrolysis gives XCO3 compound. This XCO3 on reaction with alkalis like sodium hydroxide, that produces this compound. This is called as HXCO4 minus, called as xenate ion. So this xenate ion or sodium xenate further reacts with NaOH. So I'm writing here excess NaOH. It gives Na2 XCO6. Very important compound of xenon. The liberation of xenon, oxygen, and this is called as sodium perxenate. XCO6 2 minus ion, called as perxenate ion. This reaction is disproportionation reaction. Why I am highlighting this equation? Because The perxenate ion we are getting, no, XeO62 minus ion is very, very important. One of the important oxidizing agent in number of chemical reactions. XeO62 minus ion, perxenate ion, good oxidizing agent. XeO62 minus ion, octahedral structure. One of the very, very important oxidizing agent. Generally, we are using fluorine as oxidizing agent. On par with fluorine, this is also a good oxidizing agent. Perxenate to xenate. Xenate is HXeO4 minus. Perxenate is XeO62 minus. Actually, these xenon compounds are very good fluorinating agents. They can fluorinate number of compounds. Out of these three, a good fluorinating agent is the one having more number of fluorine, that is XeF6. So that point also I am writing here. XeF2 less than XeF4 less than XeF6. Fluorinating capacity. This XeF6 has how much fluorinating capacity means it can attack SiO2 also, silica. That's why a glass container is not suitable for the storage of XeF6. XeF6, it can attack glass also. It can fluorinate glass. Glass main compound is SiO2. So XeF6 attack SiO2 and finally gives XeO3 and SiF4. SiO2 converted into SiF4, that is fluorination. Hence, glass containers are not suitable for the storage of XeF6. Another property shown by fluorides of xenon: fluorination capacity, fluorinating tendency. XeF6 good fluorinating agent because of more number of fluorines. Best example, it can attack glass also, and SiO2 converted into SiF4. That's why glass vessels or glass containers are not suitable for the storage of XeF6. And finally, along with fluorides, we have two important oxides also. One is XeO3, another one is XeO4. XeO3 is sp3 with one lone pair. XeO4 is sp3, no lone pair near central atom. So both xenons sp3, but this is pyramidal. This one tetrahedral, but my requirement is pi bonds runner. In both compounds, all pi bonds are d pi p pi. No p pi p pi bonds. All pi bonds are d pi p pi. ఇక్కడ 3 pi bonds d pi p pi. And here 4 pi bonds and d pi p pi bonds. These are the few points related to xenon compounds. Mainly with the structure nana. A new structure, square antiplasmatic, and they can react with fluoride donors and fluoride acceptors. And another set of reactions are hydrolysis reactions. Complete hydrolysis and this one, partial hydrolysis of XeF6 gives two intermediate compounds, XeOF4 and XeO2F2. And this one, xenate ion formation, one of the good oxidizing agent among known compounds obtained from XeF6. First complete hydrolysis followed by reaction with excess sodium hydroxide. Right, Anna, tomorrow we'll continue remaining.